Okay, hi everybody. Today we're going to start talking about nuclear physics. So, study of nuclear physics really began very early 1900s. I just wanted to remind you of the scale of the known universe that we study here in physics. It goes all the way up to you're looking at things like galaxies and stars. Our scale is about, on the meter scale, 1 meter. Earth, you're talking about 10 to the 6, right, for the radius of the Earth. Then when we start looking at light, we're down to the nanometer scale. Now we're going to get down into the 10 to the negative 14th, 10 to the negative 15th scale when we talk about the nucleus. So that's a wide range. So another thing I wanted to remind you is now when we start talking about the nucleus, we don't talk about masses in terms of kilograms. So for example, the mass of the proton, it's about 1.6726 times 10 to the negative 27 kilograms. But we'll use relativistic masses, so we'll use mc squared usually. So we'll say a mass in MeV. So for example, the mass of the proton, c squared, is equal to about 938.27 MeV. So many times we just refer to the rest mass energy. So about 1911, Ernest Rutherford at Manchester University a young professor who had studied under J.J. Thomson at one point, along with his students, or one's a postdoc, I think, Geiger and Marston. I think Geiger is the postdoc. We're looking at scattering particles from nuclei. Now, Rutherford had his hand in the beginnings of radioactivity, and he was shooting alpha particles that came from, I think, radon is probably what he was using, at nuclei. So he had a scattering experiment, the 2+ charge of the alpha particle. And then he had a big nucleus it was scattering off of. Now, the model that they had, of course, at that time, it's known as the plum pudding model, was that you had a positive cloud of charge. And embedded in it, moving around in orbits, were electrons. Now, according to this model, as you go through, you start hitting, once you get into the positive charge, there's really no net charge on the alpha particle. It sees electrons here and here randomly. So when it comes out, if it does go through there, it should not scatter very much at all. Now, the model at that time, before these scattering experiments, it accounted for the polarization of atoms. It took into account that it was harder to remove successive electrons from the atom. So in general, it matched the experimental data they had at the time. So we make fun of it now, but it did match the data until Rutherford's experiment. So as you know, Geiger and Marston came to Rutherford and said that every once in a while the alpha particle went towards the nucleus and then came straight back. Not very often, but every once in a while. So that was an indication of a very small but solid nucleus, and Rutherford knew that. I thought we should just take a a minute to use that to estimate how big a nuclei might be, because that just gives you your first idea of the nucleus. So let's see how close this alpha particle should get to the nucleus, and we can use that as an estimate for the size of the nucleus. So I'm sure that Rutherford probably used radon 222, but you can use, we could, for example, americium 241 that's found in smoke detectors has an average kinetic energy of about 5.5 mega electron volts. So we can use that as our idea. So all the kinetic energy of the alpha particle gets transferred into potential energy. It gets close to our gold nucleus when it stops here. So that distance is going to be our estimate. Our nuclear, we'll call it the radius of our nucleus. So the kinetic energy is 5.5 MeV. I'll just write it as Ke right now, equals the constant, so this is the electric potential energy. We have the charge of the alpha particle, the charge of our atom, in this case it was gold, over. So if we solve, our nucleus is approximately, it is equal to 2 in this case. Kinetic energy on the bottom, let's see, big K, Q alpha, Q gold, over Ke. That's equal, we put in our numbers, K is 9 times 10 to the 9, I won't bother with units at this point. Charge is 2e for the alpha particle, 79e for gold, over 5.5 times 10 to the 6 eV, and 1 eV is 1.6 times 10 to the negative 19 joules. So and then I'll put in the value for E, which is 1.6 times 10 to the negative 19. When I stick that into my calculator, I get 4.1 times 10 to the negative 14 meters. So that gives you an idea. So that would be a very big nucleus, right? So let's take a minute and talk about how do we actually measure the radius of something so small as the nucleus. So you've probably before used light to probe very small things. You'll find out from Fraunhofer diffraction. If we want to see something very small like a blood cell and we shoot light at a certain energy at it, it makes a pattern of, if you look on the screen, you have dark areas and white areas, and where it's dark, where you don't have any light, if you take a cross section of that, what you'll see is bright, dark, bright, dark, bright, dark. And there's a formula. So here we had the light. Here's the target. Oops, sorry. Let's start that over. Okay, So when we want to measure, let's say, the diameter of something like a blood cell, what we do is we shine light at it at a certain frequency, certain energy of the light, and then we have a screen behind there, and it makes a pattern where the intensity might go, it might be very dark and then light. So this is the intensity of light as you go. So you get some pattern. It's called Fraunhofer. We use this. Sorry, it's called Fraunhofer diffraction. And if you measure from the target some angle to where, let's say, where you have dark fringes, so here's some angle theta for the minimums. There's a formula, sine theta for the min is equal to 0.61 times the wavelength of your light. So this is also equal to hc over lambda over the radius of the object. Okay. So this works for light, but it also works for something the size of the nucleus, which is much, much smaller than a blood cell. So there's our blood cell. Nucleus much, much smaller. So instead of light, we use something else that has a wavelength associated with it. We use an electron. That has a certain energy, and we get the same type of pattern. So let me show you a graph. So these are some studies done in 1956 from the Reviews of Modern Physics. The author is Hofstadter. So the target was an oxygen 16, and the electron energies are given here: 360 MeV, 420, and this was carbon 12 plus here. So here's the first minimums for this. Here's the minimum for this. Here's that first minimum for this. So we can use that. Let's do an example. Let's use that Fraunhofer diffraction formula to find the approximate radius for this O2 using 360 MeV. So we need the minimum at that angle for the minimum, and to me that looks like it's about 53 degrees. That's what I'm going to use for my approximation. Okay, so if I solve that formula for R equals 0.61 times lambda sine of 53 degrees. This is for 360 MeV electrons. Okay, well, those electrons have a de Broglie wavelength, so that's what I need to put in there. We have this formula from de Broglie. That means I can find lambda equals h over p. So I need the momentum of these electrons. But these electrons are generally relativistic. So we have to use Einstein's. Einstein, using this, the energy is equal to the square root of the momentum times c squared plus mc squared squared. From this you get pc squared equals e squared minus rest mass c squared squared. Okay, so that's equal to That's 300, and this is in MeV. This is 360 squared. The rest mass of the electron is 0.511 MeV squared. So then that's really just approximately 360, 0.511 squared. If you square this and square that, this one's not really going to matter. So P is about 360 MeV over C. And when I do that, 360 times 10 to the 6, so I'm going to get my momentum in SI units. EV times, I know 1 EV is 1.6 times 10 to the negative 19 joules. And I do C is 3 times 10 to the 8 meters per second. So this will give me a momentum in kilograms times meters per second. And when I stick it in my calculator, I get 1.92 times 10 to the negative 19 joules per second over meters, which is a kilogram meters over second. All right, so now I can calculate the wavelength. Go back up here. Here's the wavelength formula. So my wavelength is going to be Planck's constant, 6.63 times 10 to the negative 34 joules times seconds, over what we just found for the momentum, 1.92 times 10 to the negative 19 kilograms meters per second. Or I could have kept it in joules, probably do that joules per second over meters. How about that? So you can see the joules and seconds cancel out, and I'll be left with just meters. And this gives me 3.45 times 10 to the negative 15 meters. So that's the wavelength, 3.45 femtometers. So 10 to the negative 15 meters is what we call a femtometer. Okay, so now I'm ready. R equals 0.61 times 3.45 femtometer. I can just use my units will be femtometers here then. Sine of 53 degrees. I get 2.64 femtometers. So that's what I get for the radius of the isotope oxygen 16. So it's an oxygen atom. It has 8 protons, of course, that otherwise it wouldn't be oxygen, and also 8 neutrons. Okay. So do we have to do electron scattering to get the radius of any nucleus? And the answer is no. Studies from the electron scattering, so from Hofstadter, this was from the Review of Modern Physics is what it was from. Volume 58, page 214, this was 1956. Studies from electron scattering seem to give us a formula that we can use for the radius of this. And it's 1.07 plus or minus 0.02. And then you take A, which is the atomic mass number, A to the 1/3 power, and the units will be femtometers. So if you stick in our number, A is 16 for us, so R for 16, according to this, would be 1.07 times 16 to the 1/3 femtometers, and gives us 2.70 femtometers. And let's see, what What were we estimating from the diffraction? We got 2.64. So this formula gets pretty close. Now, from beta decay studies, when they look at electrons being emitted due to beta decay, they get a slightly different formula that they use. So this from beta decay. They get R is 1.2 plus or minus 0.2, so a bigger uncertainty. Femtometers. No, what am I doing? It's wrong. It's R naught is 1.2 femtometers plus or minus 0.2 femtometers, and R is R naught A to the 1/3. But we're going to use these results. We're going to use this. That seems to be, this assumes a uniform charge distribution. The charge distribution in atoms doesn't seem to be uniform. I think this is the better choice for the estimate of your radius. Okay, now just to remind you, now that I talked about the atomic mass number, we tend to write for a nucleus, put the nucleus in this form X, and this could be the symbol for it, like H for hydrogen or He for helium, and then we put down the atomic number here. And we put in up here the atomic mass number. So the number of, that's the number of protons. And this is the number of protons plus number of neutrons. So when we have oxygen, we really don't, since we use the symbol, oh, you're supposed to know that there's 8 protons in there, but there's different isotopes of oxygen, so that's a different isotope. For carbon, carbon 12, carbon 14. Okay, so these are different isotopes of the same element. So the next thing we want to do is look at how tightly the nucleus is bound together. How much energy is required to break that nucleus apart? So here's a graph of known isotopes, and it's on this axis it's the number of neutrons, and on this axis the number of protons. The stable ones are in black, and then outlined in these blue there's isotopes in those ranges that are not stable. This line here is if you had just as many protons as neutrons, this would be the line that you would follow. So for a number of protons for atomic numbers less than 13, it pretty much follows that line, but then as you go above atomic number 13, it deviates. What this means by deviating in this direction from that line means you have more neutrons than protons. So what does that mean? Why is that? Well, it's because you have the Coulomb repulsion between protons, and you have a nuclear force, and we call it the strong nuclear force that is holding the nuclei, the protons and the neutrons together. So the strong nuclear force acts between neutrons and protons, but it acts on a small range, so on the order of 10 to the negative 15 meters. So if you put neutrons between protons, So here is your proton. Here's another proton, but if I pack a neutron in there, the Coulomb repulsion goes down a little bit because they're not so close. And the strong force still holds that proton and that neutron and that neutron and that proton. So the big nuclei will have lots of neutrons and not as many protons. But when you get big enough, the nuclear force just can't act across a huge range. So the nuclear force range, I said, was on the order of 10 to the negative 15 meters. So when you get nuclei that are too big, they're not going to be stable. So that's what you see on that graph is at the higher atomic numbers, they're, especially the man-made atoms, there are just none that are stable. Doesn't mean they will just fall apart all the time, but they might have a half-life for a long time, but they are unstable. So it turns out that if you take the nucleus and you add up all the protons and take all the mass of the protons, and you add up all the neutrons that you have, which is A minus Z, mass of the neutron, and if you add that up and you subtract the mass of the atom, and actually since we usually look at the mass of the atom, that includes electrons, instead of the mass of the proton, in practice we usually take mass of hydrogen, then you'll find there's a difference in energy. So in fact this mass of the actual atom is smaller than the mass of the constituents. So what happens? What happens to that mass? So there's a mass difference. Well, you remember from relativity that E equals mass c squared. Mass is equivalent to energy. That mass got converted into energy, binding energy, to hold the nucleus together. So if I take this mass of neutron c squared minus mass of the atom c squared equals the binding energy. So let's calculate the binding energy for some nucleus. Now in your Appendix A in your book, they have masses of different nuclei. They are in atomic mass units. So what you can do in that case is take Z times mass of H plus A minus Z, mass of the neutrons in atomic mass units, minus mass of your atom in atomic mass units. And you take all this, and one atomic mass unit is 931.494, I think, mega electron volts. So you can convert this into mega electron volts. That's like putting a c squared and everything, but we just kind of ignore that. So according to your book, the mass of hydrogen is 1.00798 U. Mass of the neutron is a little bigger, 1.00865 U. 8665. U. Okay, so I'm going to pick for my atom uranium 238. The atomic number for uranium is 92. The mass of this, according to your book, is 238.050784. So that's the most common isotope of uranium. So let's see if we can calculate the binding energy. So we have 92 hydrogen atoms if we include electrons. So 92 times 1.00798 plus, then we have 238 total protons and neutrons. So that means 146 neutrons, which are 1.008665 U. Take that minus 238.050784, and we multiply all that by 931.494, and this should have units of MeV then. Okay. I get a difference of, in the brackets here, it's 1.948466. So, and then I need to multiply that by 931.494. So it looks like 181,498 mega electron volts. So 181,498 mega electron volts. That is a lot of energy. No, I wrote that down wrong. It's 1,814.98 mega electron volts. So we'll just use 1,814 mega electron volts. That's better. Okay. So that seems like a lot. So, of course, the binding energy to hold U-238 together is going to be much more than something like iron, right? I mean, iron has atomic number 26. So, and uranium's got 92 protons. Uranium is a much bigger nucleus, right? So it's going to have bigger binding energy, more binding energy to hold it together. But that doesn't mean it's more stable than iron. Matter of fact, iron is the most stable element. And why is that? Well, it's not really, of course, bigger nuclei are going to have bigger binding energies. You're holding more together. But what stability depends on is the binding energy per nucleon. So binding energy per nucleon. So for us, for our uranium-238, there's 238 nucleons. So 238 divided by, 1,814 divided by 238 is 7.62. So there's that much energy per nucleon in the nucleus that's binding it together. Now, if you look at this graph, this is binding energy per nucleon versus the atomic mass number. But uranium's 238, it's way out here, it's not even on here, but you can see this is sloping down. And you see iron is over 8.5, it's something like 8.7, it looks like, per nucleon. So it's bound much more tightly. So as we're going to be getting ready to talk about radioactive decay, you should realize that if an atom's over here on this curve, if it breaks apart and gets smaller, it's going to go this way and get more stability, get more tightly bound per nucleon. And if you have something over on this side, well, maybe it would like to get bigger so that it goes towards iron here. So this is where our peak is. So that's it for this lecture. The